All right, so what we're going to learn in this lesson is we're going to learn about what is called average rate of change. Okay, I'm going to teach you how to calculate the average rate of change in some sort of situation where a variable is changing. Okay, well, what is average rate of change? Well, one way of thinking about it goes like this. It's a situation where you substitute a constant rate of change for a situation that involves a variable rate of change. Okay. Because constant rates of change are easier to calculate and easier to understand, and they require a little less information, you can use a constant rate of change to represent a situation that involves a variable rate of change. Variable rates of change are a little more complicated, and you learn about how to understand variable rates of change in a calculus class. So if you're not in a calculus class yet, or if you're just somewhere near the beginning of learning calculus, average rate of change can be really helpful for you to understand a complicated situation by using a simpler situation. All right, so I'm just going to go over how to calculate a constant rate of change, which is something that you already know how to do. You don't know that you already know how to do it, but you do already know how to do it. Very simply, calculating constant rate of change means calculating slope. That's it, calculating the slope of a line. So hopefully you have recently reviewed how to calculate the slope of a line. Okay? Now lines can take on a couple different forms. There's slope-intercept form, which is y equals mx plus b. And then there's point-slope form, which is y minus y1 is equal to m times x minus x1. Now, when we say calculating a constant rate of change, all we're doing is calculating the m. That's all we care about, is just the m. And what you may have reviewed or may remember is that to calculate m, all you have to do is calculate the change in the dependent variable, or change in y over change in x. Okay? Now, it doesn't have to be y and x. It can be change in d over change in t. There's a lot of different possibilities that you can have. But as we understand it on a coordinate plane, it's change in y over change in x, which is also given by y2 minus y1 over x2 minus x1. Okay? And in order to do this, you need to have 2 points, 2 coordinates. So let's say, for example, you have the coordinates 4, 19, and the coordinates 7, 52. Okay? So if you wanted to know, if you were told that these 2 points that are on a line, a straight line, because constant rates of change are associated with linear graphs, okay? That these 2 are on a straight line, all you'd have to do is take one of the y values, let's say 52, and subtract away the other y value, 19, divided by the x value that went along with that first, or that y value that you put in. So the x value that goes with 52 is 7, minus the x value that goes along with the other y. The y value, or the x value that goes with 19 is 4. And so all we'd have to do is 52 minus 19, which is going to be 33. And then 7 minus 4 is 3. And 33 divided by 3 is 11. And therefore, the constant rate of change of this line is 11. And we could write the equation of the line using point-slope form. We can say y minus, we'll use this point right here, y minus 19 is equal to the slope, 11, times x minus the x value that goes with 19, which is 4. And this is the equation of the line that these 2 points pass through. Now, here's the thing about an average rate of change. Now that we know how to calculate, that calculating a constant rate of change basically just means calculating the slope of a straight line. But what we said before is that an average rate of change is where we substitute this rate of change in for a situation where we have a variable rate of change. And that's what we're going to move to right now. All right, when you calculate an average rate of change, you're calculating it over a limited interval, okay? And when I say limited interval, I'm talking about input values, okay? So, and what we call this interval, there's a starting value and then there is an ending value on the interval. The starting value is usually referred to as by the letter A. A is the starting input value. Input value. Remember that input values, in functions and on the coordinate plane are usually represented by the x variable, right? And then b is the ending input value. All right? And so what we'll do is we'll represent the interval, let's say with brackets, and we'll say starting at A and ending at B, from this up to this, okay? And then what we'll do is we'll have the thing that's changing that we care about, okay? And so usually a function, let's say f of x, represents the changing output variable, okay? So, for example, let's say that f of x is representing the distance that a car has traveled on a trip, okay? So let's say we have and we'll make a table of values here, and let's say that x is representing hours traveled, okay? Hours traveled, and f of x is representing distance traveled, okay? So let's say after 2 hours of driving, you've gone, let's say, 105 miles. Then let's say that the next time you measure how far you've driven is after 6 hours of driving. And after 6 hours of driving, you've gone, let's say, 380 miles, okay? Then the next time you measure is after 9 hours of driving, and let's say at that point, you've gone, let's say 580 miles, okay? What we can do is we can use an average rate of change to identify the speed of the vehicle, okay? Because remember, speed is distance over time traveled, right? I should have put miles again. This is miles traveled. That is a distance, but we're measuring it in miles, okay? And the way that we can calculate the average rate of change, so let's say that we want to know what is the speed, or what was, let's say was, the speed of the vehicle at 4 hours. Okay, at time 4 hours. Now, 4 is between 2 and 6. We don't have a record for how fast the vehicle was going. In fact, we don't have a record for how fast it's going at all here, but we can use the hours traveled and the distance traveled to calculate the speed of the vehicle by calculating an average rate of change, okay? And the way that we're going to do this is we're going to use a formula. The average rate of change is given by the output variable, f of x, but we're going to plug in the ending time, and we're going to subtract away the output variable from the beginning time. And then we're going to divide it by b minus a. I want you to understand that what you're looking at here is the same thing as y2 minus y1 over x2 minus x1, right? Because a and b are x values, and f is the output function, right? So f of x is like the same thing as y. Well, when we plug a into f of x, we get the output value at the beginning, and then when we plug b in, we get the output value at the end. So what we're essentially doing here is ending output value minus beginning output value divided by ending input value minus starting input value. Okay, so here, if we want to know what the speed was at 4, we need the a time that started before 4. That'll be the starting time, 2. Call that A. And we need the ending time after 4, which is going to be 6. So we're going to call that B. So in this case, A is 2, B is 6. And since f of x is this column here, 105, well, that's f of A. And 380, that's f of B. And so we're going to use this formula. We're going to go f of B minus f of A, which is 380 minus 105. That's a 0 right there. Over B minus A, 6 minus 2. So 380 minus 105, that's 275. Over 6 minus 2 is 4. And we can just, this can't be reduced, so we can just say 275 over 4 miles per hour, or we can grab a calculator and we can do, if we want a decimal answer, which in many cases we will, we'll do 275 divided by 4, which is 68.75 miles mph, miles per hour. Okay? And that is, now understand, this is probably a variable rate of change. In reality, when you're driving on a, you're looking at the speedometer, right? Okay? And it'll say 47 miles per hour, 1 minute, and then 3 minutes later, it says, 49 miles per hour. And as you drive, your speed increases and decreases, right? So if you've driven in a car before, you're looking at the speedometer and it's changing. As you push down on the gas and lift up on the gas, your speed is actually variable. It is not staying the same. Now, if you set the cruise control, it'll mostly stay the same, but as you go up and down hills, you know that the speed will go down by half a mile an hour, it'll go up by 1 mile an hour, even with cruise control. So your speed on the road is always a variable rate of change. Well, what we're doing here is we're using an average rate of change to approximate a variable rate of change. We're using a constant rate of change that we calculate by the slope of a line in place of, to substitute for a variable rate of change. We have no idea how fast the vehicle was traveling at 4 hours, so we're basically guessing how fast it could have been driving. And so that's why we use this f of b minus f of a over b minus a slope formula, to estimate average rate of change. Now what we're going to do is I'm going to show you a couple different ways I want you to be able to calculate average rate of change. All right, so this is the most basic kind of question that you have to be able to answer. Here's our formula up here, f of b minus f of a over b minus a. That is our average rate of change formula. And what this says is, the question says, is what is the average rate of change of f of x, which is the analytical function is natural log of 5x, on the interval from 3 to 11, okay? And very simply, this is how you're going to do that. You're going to grab a calculator. And now you don't have to do it in a calculator. If you don't have a calculator, then you're just going to represent it analytically. And here's what we're going to do. We're going to replace f of b with the function. The x is going to become a b, but then you're going to put a number in for the b. So what we're talking about here is take your function and put it in there. It's going to become the natural log of 5b minus, now we're going to put natural log of 5x in for f of a, but we're going to replace the x with an a, minus the natural log of 5a over b minus a. Okay, well, what are b and a? B and a come from our interval, from 3 up to 11. So a is always the starting value and b is always the ending number, right? So a is 3, b is 11. So what we now have is the natural log of 5 times whatever b is, which is 11, and 5 times 11 is 55. So it's going to be the natural log of 55 minus 5 times, okay, a is 3, 5 times 3 is 15, so minus the natural log of 15 over b is 11 minus a is 3. And so now all we have to do is we can just say the natural log of 55. Now, I want to remind you something. You may not remember this, but we can actually simplify this. Okay, so when we are subtracting logarithms, we could actually do the natural log of 55 over 15 because of the properties of logarithms. Or you can do it in a calculator, right? And 11 minus 3, that's going to be 8, right? So let's grab a calculator. Where did I put that thing down? There it is. And we'll do natural log of 55. And there's a button on the calculator that says ln 55, close parenthesis, minus ln of 15, close that parenthesis. Then I'm going to hit enter. Then I'm going to hit divided by 11 minus 3, that's 8, right? So divided by 8, and it says that the average rate of change here, or this right here, is 0.1624. And so this is the average rate of change of the function natural log of 5x on the interval from 3 to 11. Okay? Now, what you would learn later in a calculus class is that this is actually the slope of what is called a secant line, a line that connects a curve between 2 points. And I'm going to show you that in just a minute when we do a graphing example. All right, so what I've done here is I have projected a graph, a curve, up onto the board. And the fact that it's a curve means that it has a variable rate of change. Okay? We're going to call this curve g of x, and it doesn't matter what the function is. We only need the graph to be able to calculate this. But what this says is, what is the average rate of change of g of x on the interval from 3 up to 5? Now remember, these are x values. So these are independent variables going from here to here. And over here is 3, and here is 5. Well, in order to use our formula, this 3 and the 5, they're going to go in the denominator. The 3 is A and the 5 is B, right? So we're going to put a 5 here and a 3 here. But what we need to do is we need to know what the output values are of this graph when we plug in 3 and when we plug in 5. So we need the output value for 3 to go right here and the output value for 5 to go right here. Well, we can get them directly from the graph. If we go to 3 and go up to the curve, that's right here, right? So this is the point 3, 2, right? All right, so the input value is 3, the output value is 2. When we go to 5, the input value is 5, and the output value is also 5, right? And so I can show you how to calculate this. We can calculate this very easily using the formula there, but something else that I want to show you is this. Is that what we're basically doing with an average rate of change is, even though that this graph is curving from here up to here, the rate of change is actually changing. What we're doing is we are substituting the slope of the straight line between the 2 points. So we're going to use the slope of this line, m, okay, whatever the slope is of this line, and then we're going to pretend that that is the rate of change or the slope of this curve, even though that it's changing from here to here. Okay, that's the basic idea of an average rate of change. All right, well, how are we going to get that number? We're going to use that formula up there. We need the output at 5, which is 5, minus the output at 3. If we were to plug 3 in, the output would be 2. See this? See, we're doing y2 minus y1 over x2, which is 5, or b, over x1, which is a, which is 3. So 5 minus 2, that's 3. 5 minus 3 is 2, which is 1.5. And so the average rate of change of this function between 3 and 5 is 1.5. Okay? Okay. So now this example is called a numerical example. The first example I gave you was analytical. I actually gave you the function. All you had to do was plug it in to the formula, plug in the numbers, and then use a calculator. The one we just did was a graphical example where you had to look at a graph and get, using the input values, you had to go up to the curve and get the output values. Now this is what's called a numerical example, where I actually just give you the input values and the output values, but you have to decide which ones that you need to use. Okay? So this says that h of t, that's h of t is the height of a tree as it grows in my backyard over several years, t. So t is time in years. So When I first plant the trees in my backyard, they're 3 feet tall. Why? Because I bought them as 3 feet tall from the nursery. Okay? After 2 years, the tree is 6 feet tall, or one of the trees, the one in question here, the tree is 6 feet tall. After 4 years, it's 11 feet tall, and after 6 years, it's 15 feet tall. Now what we're asking at what rate was the tree growing? So now we want to calculate a rate of change. Well, the way we calculate a rate of change is we use the average rate of change formula here, okay? Now it says at what rate was the tree growing at 5 years? Well, you may say, well, 5 isn't on the graph. Okay, so what you're going to do is you want to show where 5 is. 5 is supposed to be right here. And what you do is the number right before it, the smaller number before it, which is 4, that becomes A. And the next number after it, which is 6, that one becomes B. And now your output values are the H of T values. These are the inputs, and this would be F of A, and this one over here would be F of B. So this is F of A, and this over here is F of B. But it's actually H of A and H of B, okay? So our formula now changes. Instead of F of B minus F of A, it's H of B minus H of A. Why? Because the function is H of T instead of F of X over B minus A. Now, what is the output value? You know, B is 6. And what is the output value? What is H of T at 6? Well, it's 15. So we put a 15 here, minus. And then what is the output value at A? A is 4. The output value is 11. So 15 minus 11. And then B is 6 minus A is 4. 15 minus 11, that's 4. 6 minus 4 is 2. And 4 divided by 2 is 2. We can simplify it. It might be a decimal, but in this case, it's a whole number. We also need units. H of T is in feet, right? I didn't say that. Height of a tree in feet. I should have said that from the beginning. So this is in feet. And then T is in years. So what we would say is it's 2 feet per year. Okay? So the rate at which the tree was growing at 5 years is approximately 2 feet per year using average rate of change. Okay? So I want you to be able to calculate average rates of change either if you're given the algebraic formula, the function itself, or if you're given a graph, or if you're given a table of values, you have to be able to calculate those things. Okay, that's it for average rate of change. In my opinion, it's pretty easy. You just need a lot of practice, and you should be just fine.